got my pendulum over here. So pendulums, depending on the length of the pendulum, have a certain frequency with which they go back and forth. That is the natural frequency. There's nothing that we can do except change the length of this pendulum, and it will have this frequency, this period of oscillation. Inverse of period is frequency, right? It doesn't matter about the mass of the pendulum, or mass of the bob, which is the name of the thing at the bottom of the pendulum. It's still going to have the same frequency, same period. So that is the natural frequency, for example, of a pendulum. Now, everything has a natural frequency. There's the cantilever. Depending on the length of the cantilever, there's the frequency at which this will oscillate up and down. So everything that doesn't immediately break, or unless it's made of clay, as long as it's the type of thing that does snap back to its original position, everything has a natural frequency. Now, in a certain types of oscillators, and a string is one of them, what you want to look at here, imagine that this is a very, very, very large guitar string, okay? So if you zoomed in on a guitar string and slowed the speed way down, this is what a guitar string would look like if you plucked it, okay? So I'm going to play this string, boing. All right. So even here, what you can see is actually there is a wave pulse that travels up and back and up and back and up and back the string. That's actually what happens when you pluck a guitar. It actually goes up and down, up and down, up and down, except on a guitar, it'll move at about 200 to 300 miles per hour up and down the string. And you can't see it travel up and down the string. But after a while, notice what happens to the oscillation. It doesn't take much time here. On a guitar, it takes literally 1/100th of a second before all that's left is the simple oscillation up and down, back and forth. This will happen at a certain frequency, and that it would be what is known as the natural frequency of that string. So if you pluck the guitar string, then it will end up oscillating back and forth at a natural frequency. Now that frequency, of course, changes. If I tighten the string, it'll go back and forth more quickly. Anybody who's played any stringed instrument knows what I'm talking about. Whether you play guitar, violin, bass, any stringed instrument, you know that when you tighten the string, that will make the oscillation quicker. But let's just keep the tightness the same. Also, you notice that if you played a stringed instrument, when you make the string shorter, it goes quicker. And that's why on the guitars, you have a fretboard and the fingerboard on all violin and viol class stringed instruments. Okay, we got a fundamental frequency. For strings, and this also works for air instruments, any reeded instrument as well, just about any air or string, the same thing applies, but it's a lot easier to see with a string. Okay, if I force a vibration, not the natural vibration, but if I force the vibration that's equal to a higher frequency, a very, very specific higher frequency, I can get this. Okay, this is known as a standing wave. Just a quick experience. How many people have played with a rope and got the rope to do this in any situation? Some people doing jump ropes, we'll see you can do this. You can actually do it in this way too, but I don't have enough room to do that. Okay. This is called the second harmonic. The natural frequency is the same thing as the fundamental frequency, and also known as the first harmonic. Then if I force another frequency, I can get what's known as the third harmonic. Notice that in the third harmonic, there are 3 bumps. Do you see the 3 bumps? They're going back and forth, back and forth. And then there's the spots in between, the spots that don't look like they move. Yeah, those spots are called nodes. Okay, at this point, it's hard to get any further than that, but let's take a look at this string that I've got here. Got a string, attached to the frequency generator, and it goes to a special speaker here. The speaker is attached to a post, and the post is right next to a string, causing a string to vibrate. Okay. People at home, notice I put this black backdrop here so you can see it a little bit better. But this is vibrating at a specific frequency to cause a high harmonic. Now, people who are here can see it a lot better. I'll try to see it. You can see we've got the parts that vibrate the most, and then the parts that don't seem to vibrate up and down at all. These parts right here, you notice I can even put my finger right here and it doesn't disturb the whole wave. So if we counted them up, I see I've got 1 bump, 2, 3, 4 bumps, 5, 6, and a 7th one is here off the screen for you folks at home. So there's 7 of these bumps. These bumps are called antinodes. A-N-T-I-N-O-D-E-S. These parts in right here are called nodes, N-O-D-E-S. So we got nodes and antinodes. I can tell you right now that this is the 7th harmonic that can oscillate on this string. It's easy to tell because all you have to do is count the antinodes. How many bumps do we have? As I said before, we got 1, 2, 3, 4, 5, 6, 7. 7 antinodes. All right. The harmonic frequency, the 7th harmonic frequency is 42 hertz. There is a simple mathematical way of finding out what frequency any harmonic is going to do. So let's compare this. I'm going to drop the frequency till we see the next standing wave. If it's not at one of these special frequencies, we do not get a standing wave. Okay, oh, it's coming back. See it? There it is. All right, this is, if we count them quickly, 1, 2, 3, 4, 5, 6. There's 6 antinodes, so this is the 6th harmonic. This is the 6th harmonic. The frequency is 36 hertz. Somebody at home, everybody at home, if I drop this down to try to get to the 5th harmonic, can anybody guess what should be the frequency of the 5th harmonic? Go ahead, take a guess. There we go. 1, 2, 3, 4, 5. There's the 5th harmonic. What did you say? 30. Yeah, so in other words, every harmonic is a different frequency by how many hertz? 6, right. So it's the 7th harmonic was 42 hertz. The 6th harmonic was 36 hertz. The 5th harmonic was 30 hertz. What do you think the fundamental is? Take a guess. What do you think the fundamental frequency is? There it is. The fundamental is when the whole string is just vibrating up and down with no nodes at all in between. And yeah, that is 6. So the fundamental is, again, the natural frequency. So if I just remove the driver, that's the frequency that it vibrates at. That is its natural frequency. That is the fundamental frequency. And I just have to say at this point, by the way, I just have to say that, do you know how long it took me to get this apparatus set up with this string, to get the tightness just right and the distance just right, to have the funnel be a nice round number? I spent 45 minutes just fiddling with the tightness just so you could have this demonstration. So yeah, you're welcome. Okay, what we're talking about is a form of resonance, which we'll get a little bit more into later. We're not going to have to worry about the mathematics here other than straight multiplication and division of the harmonic number. So we can ignore this whole part of the string here. Okay. So this is the string, like the guitar string, like the string that we're just looking at. And so here's the length of the string. When the string is oscillating in its fundamental tone, which is also known as its natural frequency, So fundamental tone equals natural frequency. The wave is going to be oscillating on the string back and forth between the middle of the string being at a high point and a low point. So that, again, is the fundamental oscillation of any stringed instrument. The frequency will be determined by how tight the string is, as well as the mass of the string, but you don't need to worry about that. Let's just say in this case that we measured the wavelength of this string and we found out the wavelength is 2 meters. So right here we have lambda 1. I'll write it bigger in just case you don't have this printed out. Lambda 1. That's the wavelength of the fundamental oscillation. Let's just say we measured it and it was 2 meters. Okay? Let's say we also measured, in this case, our fundamental frequency. We'll use the sample that we just used here. Let's say the fundamental frequency was 6 cycles per second, except in a normal string, that fundamental frequency would be in the hundreds of cycles per second. So hertz. So that's F1. Fundamental frequency is 6 cycles per second. Now with this, we could go ahead and measure, well, how fast? Initially, remember, a wave is actually traveling up and down the string. We could measure how fast that wave is traveling by just using our wave equals frequency times wavelength formula. Remember? Wave speed equals frequency times wavelength. You should have practiced that by now. And all we have to do is multiply the frequency times the wavelength, 6 times 2. I think you can do that in your head, 12 meters per second. Again, reminder, that's how fast the pulse travels up and down the string. That's not how fast this thing is moving up and down. Remember, we measure that in frequency, how quickly it's vibrating per second is frequency. This is talking about how fast does a wave travel up and down the string. This should stay constant for the string because any wave, the speed of the wave determined by the medium. So it's the same string no matter what the frequency is. Okay, then we're going to draw the first 4 overtones. The first overtone is the second harmonic. So we have a fundamental tone, harmonic number 1. The next one is harmonic number 2. So lambda 2 and F2. Instead of the single bump that goes back and forth, you're going to have that node in the middle. So it's easier if you draw on the nodes first. And it's going to oscillate between this position and its alternating position. Right here, I'll draw this bigger. Lambda 2, the wavelength of the second harmonic. The wavelength of the second harmonic is the wavelength of the first harmonic divided by 2. So it'd be 2 meters divided by 2, which would be 1 meter in this case. This is just an example initial wavelength. The frequency of the second harmonic would be the frequency of the fundamental times 2, whatever the harmonic number is. So that means it'll be 12. Notice that if we multiply the wavelength times the frequency, we get, in this case, 1 times 12, which is still going to be equal to 12. All right, let's look at the third harmonic. How many different bumps, how many antinodes does the third harmonic have? Quick answer, chat that in. The first harmonic has 1, second harmonic has 2. So yeah, just count the bumps, count the antinodes. So if it has 3 bumps, then there'll be 2 nodes in between them. Remember that the third harmonic is going to have 3 bumps, so it's going to be separated into 3 parts. And you can try to do this. This is kind of fun for some people, annoying for other people. Hope it's the first one. So that's the third harmonic. Lambda 3, the wavelength of the third harmonic, will be the same as the wavelength of the first harmonic divided by 3. 3 being the harmonic number. So it's going to be 2 meters over 3, which is going to be 2/3 of a meter. Frequency of the third harmonic is going to be the frequency of the fundamental the natural frequency, times 3. 6 times 3 is 18. Guess what? 2/3 times 18 is 12. So once again, frequency times wavelength is equal to speed. And the speed always stays the same. This is the speed of the wave traveling down the string. Running out of time here, so go ahead and let's just skip to the 5th harmonic, shall we? Skip to the 5th harmonic and have a go at drawing that. Remember, the 5th harmonic is going to have 4 nodes, 4 dots in between for the 5th harmonic. 1, 2, 3, 4 nodes in between. So the oscillation will be something like this, with 1, 2, 3, 4, 5 antinodes. And then you show with dotted lines the opposite form of oscillation. Okay.